All right, we are on to chapter 5 now. And we're going to talk about circular motion and gravitation. Yeah, circular motion. CM can stand for so many things. You know, centimeters, center of mass, circular motion, and all that stuff. Anyway, circular motion. Now, how is this chapter going to be different from the chapters that you've done earlier? Now, earlier, you have done things about linear motion. So everything that you did was linear motion. Things were going in a straight line, right? So you learned about linear motion and you applied the equations of motion. And after that, you made two-dimensional linear motion, which made it go like that, called projectiles. And so that was a different thing, but still it was linear motion in 2 dimensions, creating that projectile trajectory. You did that. And after that, we went on to find out like what forces are and what forces can do to an object. So how can an object be influenced by forces? So we studied that, and then we went through the first, second, third laws. And hopefully you're in a good position right now as far as learning mechanics is concerned. Now we are moving into circular motion, where things are going to go round and round. So it might create a lot of spin for some people, but then it depends. It depends. If you follow the instructions carefully, then it's just again an easy chapter. It's not going to be difficult. So just follow clearly what is the main concept of this chapter, and then you should be fine. Okay, even difficult problems and stuff like that can be approached if you exactly know what's going on in circular motion. So what is circular motion? When an object goes round and round in a circular path, right? When an object goes round and round in the circular path, that is circular motion. So you have a center, you have an object. If the object is moving round and round in a circular path, now that's the radius of the path. This object is probably having a certain velocity over there. And after a little while, it is moving to this location where it has a velocity there. Now, we are going to study uniform circular motion for the time being. So uniform circular motion. Now, when you say uniform circular motion, it means circular motion of objects with a constant speed. Okay? So the speed is the same everywhere. The speed is the same everywhere. So when it goes from here to here, it is going with the same speed. Are the velocities the same?
No, they have a different.
Yeah, they have a different velocity. So the velocity here is v1 and the velocity is v2. Why are the velocities different even though the speed is same? Because of the direction. It's changing direction continuously. So because it is changing direction, it is definitely suffering a change of velocity. You can see that clearly. So the velocity's magnitude is the same everywhere because it's going at a constant speed. The two lines imply magnitude. So velocity, but v1's magnitude is the same as v2's magnitude, which is just v, the speed. Okay? Velocity's magnitudes are same everywhere because it's going at a constant speed, and the speed is v. As it is moving in a circular path, it is covering some distances. It is covering some distances along the curve, the arc length. There is a radius here, and it describes angles, theta. So theta is the angle described, and S is the arc length, and R is radius. What is theta measured in? Radians. You know the SI unit of theta is radians. Angle is measured in radians. Now, what is this radian? What is a radian? So write down the definition of radian. Write down the definition of radian. One radian is the angle subtended. One radian is the angle subtended by an arc. One radian is the angle subtended by an arc. One radian is the angle subtended by an arc whose length is the same as the radius. Okay, so one radian, so this will be one radian now. So one radian is the angle subtended at the center of a circle by an arc whose length is the same as the radius. Okay, so that's the definition of a radian. So it has a definite, a meaning. Degree doesn't have a real meaning. It is just like somebody said, okay, let it be 90 degrees. And so we kind of use it as a scale. But it is not really a scientific unit. A scientific unit is having some geometrical proportions there. So any angle where the arc length is the same as the radii, that is called one radian. So, in one circle, in a circle, if you take a circle of a certain radius, let's say 10 centimeters. If you take a circle of radius 10 centimeters, okay, and if you cut off exactly 10 centimeters along the arc, like that. If you cut off 10 centimeters along the arc, so that's also 10 centimeters. This angle is 1 radian. Now, if you cut off once again, that's a 2nd radian. If you cut off once again, that's a 3rd radian. If you cut off once again, that's a 4th radian. If you cut off once again, that's a 5th radian. And if you cut off once again, that's a 6th radian. And then there's a tiny bit of angle left. And that angle is 0.28 radian. That is true for any circle. This angle will be 0.28 radians. So what's the total angle in the whole circle? 6.28. So total angle is 6.28 radian. And that's what we write as 2 pi. What is written as 2 pi is the angle at the center of a circle in radians. Okay? So 2 pi, we use that 2 pi so many times, like pi. So what is pi? Pi is half the circle angle. And what is, so this is 2 times 3.14. Okay? So the 2 pi is the total angle subtended at the center. So what is the definition of angle? So now you know that the total angle is always going to be equal to 2 pi for a full circle. This is true for anything, for the earth, for any circle, you're going to have the same thing. So if you cut off exactly the same distances equal to the radius, you'll end up with a little space, and that will subtend an angle of 0.28 radians for any circle. So what is the definition of angle now? Angle definition. What is the definition of angle? Angle is defined as the ratio of arc length to radius. Ratio of arc length to radius. So ratio of arc length is S over radius R. This is the definition of angle. That's the definition of angle. Angle theta is equal to S over R, and the theta will be in radians, not in degrees. And this equation is also sometimes written this way: S is equal to R theta. It's the same thing. S is equal to R theta, which means the arc length is equal to radius times the angle. In geometry, sometimes you may need to determine how much is the arc length, and then you need that equation, right? So suppose you have to lay a fence. You know what I'm saying? So you have a kind of a equal length here and here, and you need to kind of make a fence. And if you want to know exactly what length of fence is required along the arc, that equation will tell you what. Okay? Now, what is the complete distance? What is that? How do you get that? See, what is the total angle in a circle? 2 pi, and 2 pi times r gives you circumference. You already used that equation multiple times. From where that equation is coming is from the definition of angle itself, right? So what is circumference? 2 pi r. How is it 2 pi r? There it is. Circumference is 2 pi times r. Now what's the unit of angle? You know it's radians, but what's the unit of distance? Meters. What is radius? Meters. So meter over meter is what? Nothing, right? Meter divided by meter goes off. So theta does not have a unit. But then how do you represent an angle? That's why we throw in this radian, right? The radian is not actually a unit. It's just a representation. That's why when I listed the basic units, remember? I told you all about kilograms, meters, and seconds, and moles, and all the different units. And later on I said angle, radians. That is a kind of a subsidiary unit. It's not actually a unit, but it has to be considered as a basic too. So theta is equal to S over R is an equation that will be very commonly used. S is equal to R theta. So because we are talking about circles, so we need to know exactly what's the connection between this. Now theta is also called angular displacement. Because when you're talking about something that's moving round and round, we're talking about theta as a kind of displacement. It's not a linear displacement. This is a linear displacement. But this is called the angular displacement. It describes angles. So when something is spinning, it describes the angles. And so we call it angular displacement. Unit, radians. Okay? Any questions so far on radians? Now, how do you change from radians to degrees? From degrees to radians is something that you need to know too. So 2 pi radians, you know, is 360 degrees. Or pi radians is 180 degrees. And therefore 1 radian will be 180 over pi degrees. So if you want to go, if you have the radian angle and you want to find the degree equivalent of that, what do? You multiply by 180 and divide by pi. And the other way around, 1 degree is how many radians? You multiply by pi and divide by 180. So if you want the degrees, multiply by 180 first and then divide by pi. You want to get into the radian thing, so multiplied by pi and divide by 180. Make sense?
Yeah.
So this is a conversion thing. So if you want to convert from one to the other. And you know approximately what is a radian? A radian is approximately 57 something degrees. So if you have that in mind, you will know how the conversion goes. So 1 radian is 180. What is 180 over pi? 57.3 approximately is the angle. That was that. Okay? It's not 60 yet. Just a little short of 60. That is the angle. How do you, let's determine the angle subtended by the entire United States at the center of the earth. How do you do that? So that's the entire earth. Now United States on the globe, United States is from here to here. How much angle is subtended by US at the center of the earth? Okay? So US is from here to here. What is it? What length? What is the arc length? Any idea what is the distance from east end to west end?
4,500.
I don't know. You can look it up. Look it up. Look it up and find out. It is definitely not 5,000 miles.
How many radians did you say every one?
Of the? Which one?
How many radians? That's the grade.
Oh, 57.3. One, no. 1 radian is 57.3 degrees.
2,800.
Yeah, it depends from where to where it is. So
Are you going from like Maine to Southwest?
extreme to extreme. Take extreme to extreme. Approximately 2,800 miles.
3,000.
So
It looks
two.
like you were a little off. 2,800.
Oh, the shortest is 2002.
Okay, 3,000 miles.
Obviously.
So if it is 3,000 miles, the total arc length. What is this distance? What is the radius of the Earth? In miles. 4,000 miles. So the radius is 4,000 miles. That means if you dig in 4,000 miles, you go to the center, you keep digging, another 4,000 miles you reach. Alright, so 4,000 miles. Now this is the angle. Can you find the angle in radians first? So how do you find the angle? Angle is equal to S over R, which is 3,000 over 4,000, which is 0.75 radians. But again, 0.75 radian does not actually, give you a picture of the angle. So what do? Convert it to degrees. So how many degrees is that? 42.9. So approximately 43 degrees is the angle subtended by the entire United States at center out of 360 degrees. Okay. Questions? Yes. This one 2 degrees. Multiply by 180 because you want to get degrees. So multiply by the degree part of it. That is 180 divided by pi. 0.75 times 180 divided by pi. That's how you can easily convert. Now, why do we convert? Is because we need to see and understand exactly. And sometimes you may be given an angle in degrees, and you want to find out this. So if I give you this angle in degrees, and then that one, so you can actually find out how far it is, not by using degrees, but you have to convert it to radians. This angle, this equation is true only if this angle is in radians. Yes.
Does it matter what mode we're in? Degree or radian?
Doesn't matter. See, mode is important only when you use trigonometric functions, right? When you're putting sine, tan, and cos, then the mode becomes important. Now, how is the mode important? Normally, we measure angles in degrees. And so sine of a certain angle in degrees, if you're going to put sine of 30 degrees, then your mode should be in degrees. Now if you're going to put the same thing as sine of pi over 6, pi over 6 is 30 degrees, right? Pi is 180. 180 over 6 is 30 degrees. So instead of putting sine of 30 degrees, put the calculator in the radian mode and plug in sine pi over 6, it will become the same thing as 0.5. Sine 30 is 0.5, sine 30 degrees is 0.5, sine pi over 6 also is 0.5, as long as your mode is in radians. So if your angle is going in radians, then your mode should be in radians. If your angle is going in the trigonometric functions in degrees, then your mode should be in degrees. That's the rule. So in these kind of calculations, you don't have to worry about the mode. All right, coming back to this again. So now we know that S is equal to R theta. S is equal to R theta. If I divide both sides by time, because it is moving from here to here, taking a certain time t, right? So if I divide both sides by time, in other words, I'm finding the rate of this versus the rate of that. What is S over t? What is distance over time? Speed. Radius is a constant. So radius stays constant. And then comes this. Theta over t. What is theta? What is theta? I told you what it is. No. What is theta? What is it? Angular displacement. Theta is angular displacement. Now, what is the angular displacement divided by time? Angular velocity. So theta divided by time, this part of it is given a new letter, omega. So theta divided by time is omega, and what is omega? It is the angular velocity. Some books write it as angular speed, if you're looking at the magnitude. Why is it angular velocity? It is a vector quantity. Why is it vector quantity? Because you can have something spinning this way or this way. Now, something spinning counterclockwise is positive, because angles are measured from the positive x-axis counterclockwise, right? And so if something is spinning counterclockwise for you, if something is spinning like this, that angular velocity is positive. If something is spinning clockwise, that angular velocity is negative. So write it down. Angular velocity is a vector quantity, and so you need to be concerned about which way it is spinning. If it is spinning counterclockwise, it is positive angular velocity. If it is spinning clockwise, it's a negative angular velocity. So counterclockwise, positive omega. Clockwise, negative omega. Okay? So now remember to call this omega and not W. Just because it looks like W, it's a very common mistake that students end up doing, is like, oh, it looks like W, what's the difference? I can just call it W. So W equal to theta over T. W, and once you use it a couple of times, it's so difficult to change over to omega. So the best thing is to use it first time properly. Now I've had students who just, they started using W, and even if they are a senior doing something, they'll call it omega, W instead of omega. So call it omega, call it the right way, and then you'll be all right. Otherwise, what will happen is you'll graduate and go after 2 years, you've gone to some university, and you'll be doing similar topics, and then you will go to your professor and say, all right, now I know this equation B equal to RW. What is that, W? Who taught you physics? That will be the question that the professors will first ask you, like, who taught you physics? Who called it W there? Now, you called it, not me. All right, so I'm telling you right now. Omega, not W. This is omega, omega, omega. So what is this omega? Omega is theta over t, the rate at which theta is changing. Sometimes you'll see they'll write it in a differential term, like d theta over dt. That's also same thing. Sometimes they will write it as delta theta over delta t. That's also same thing. Okay? So if you see delta theta over delta t, it's the same thing as d theta over dt. It's the same thing as small fraction of, in a small fraction of time, how much angle is covering. That's it. So what is omega theta over t? Omega stands for what? Angular velocity. And what is this? No. Angular displacement. Call it by the correct name. Angular displacement, and that's time. Now, what is the unit of omega? What's the unit of this?
Nothing.
Radian. It is nothing, but I can't write nothing there. So I need to write. So that's the reason why we call it by. But we have to call it by something. You're right. It is nothing. But if I write nothing over there and then only write at the bottom something, it does not signify what you're trying to measure. So therefore, in order to relate to what you're measuring, it's better to kind of write something. That's why that something is radian. Divided by? So, oops. So radians per second, that's what is unit, radians per second. This is how we write it. The unit of omega is radians per second. And how do you find the angular velocity? You need the angular displacement and the time. If you get both of these, you find it. All right? Find the angular velocity of the seconds hand of the clock. Problem. Find the angular velocity of the seconds hand of the clock. Is the seconds hand going in circular motion?
Yeah, it is.
Go ahead. Then you should be able to find out. The seconds hand, not the second hand. There are three hands over there. Hour hand, minute hand, and seconds hand. So what do you need to find out the angular velocity of seconds hand? You need the angle described by the seconds hand once and the corresponding time. What is the angle described when the seconds hand goes once completely? 2 pi. Right? The angle for one full turn of the seconds hand is 2 pi. In what time?
66.
Then do it. Omega is equal to 2 pi divided by 60. Find out the answer and write it down. How much is it? 0.105 radians per second. See, when you see the unit radians per second, you can immediately understand what quantity you're talking about. Right? That's the reason why we write a unit. Now, if I say nothing over there, how can you say what it is? If I write nothing over there and say per second, now per second can be for vibrations. How many times this is oscillating per second? So that is frequency. Now, how many times is oscillating per second? That's frequency. So if I write per second only for this, I won't know what quantity I'm talking about. So when you say radians per second, immediately you know that you're talking about something going in circular motion. So 0.105. Find out the angular velocity of the hour hand of the clock. Go ahead. How much is the angular velocity of the hour hand of the clock? Angular velocity of the hour hand of the clock. Anyone has the answer? Yes.
0.52 radians per second.
Now both of these are negative answers. Remember, Because
It's clockwise.
because the clock obviously is clockwise, right? And therefore it is negative. So in terms of direction, you are supposed to have a negative sign for both. All. Okay.
The correct response is
So we have this equation. V is equal to R omega. That's an equation that connects linear speed with angular speed. That's a linear speed. That's the angular speed. And that's a radius. All right? That's linear speed. That is the angular speed. And that's the radius. The connection between linear speed and angular speed. So linear speed is equal to radius times angular. And if you look at the units, meters per second here, and this will be meters, and that will be radians per second. So meters, meters, seconds, seconds, and what is that?
nothing.
Nothing. So you don't have to worry about it. Okay? So although you can see that, this seems to be an extra unit over there, but it's not extra. It's just nothing. It doesn't have any unit by itself. Okay. Now, what is the significance of this equation? The significance of this equation, you can do one more problem on this angular speed. What is the angular, yes?
So when you're finding the linear speed, that's like the speed of the object if it were to continue on the tangent line.
Yes.
Right?
All right. When you're driving your car, there is a meter that normally people don't look at. That's the RPM meter, right? Nobody really bothers about it. The RPM standing for of the engine. The engine is rotating at that speed. So if the RPM is 3,000, how many radians per second is that? Because RPM obviously is not an SI unit of, this is omega. That is omega, but not in SI units. What's the SI unit of omega? Radians per?
Second.
Now this is not the SI unit. So what is this? 3,000 rotations per minute. Can we change it to radians per second? One rotation is how many radians? 2 pi. So multiply by 2 pi. So 3,000 times 2 pi will get me in radians. And then you have 1 minute converted to seconds. And that will be 314 radians per second. So that is SI unit. So if you're given omega in RPM, you cannot use that. You have to change it to radians per second. Yes.
If we just keep pi in there, is that acceptable, or do you want us to?
You can keep pi as long as when you're working and all. The final answer should not have pi.
Okay, because my answer.
Yeah,
is
sometimes
just
you can actually
100
keep the pi as it is, like keep it as 100 pi, and then sometimes it's possible that as you work through the process, the pi's cancel off. So it's okay, it's good for you. But very final answer should not have anything like pi. So 314 radians per second is the same as 3,000 RPM. 3,000 RPM, rotations per minute, means per second it is spinning 50 times. In 60 seconds it is doing 3,000. So in 1 second it's going 50 times. It's pretty fast. So if you look at 1 second, and already 50 times is spun. So imagine the speed. Now, If you look at a ceiling fan,
That'd be negative or positive.
oh, it depends which way it's moving.
How are you being reversed? What are you doing?
Okay.
Chris does. Chris does.
What's the other one? Oh, ceiling fan. So if you take a ceiling fan, as a ceiling fan is spinning, which part of the ceiling fan has a high omega, angular velocity? The outside one has an angular velocity greater than inside, or what's that? They're all the same. Because as the thing is spinning like this, they're all describing the same angle in the same time. So the angular velocity omega is a fixed thing for the ceiling fan. Now, what about the linear speed? Which point on the fan will be going fastest? The tip, yes. The tip is going to be really going fast. And so it's dangerous to put your finger at the tip. If you have to stop the fan for some reason, if you have to physically stop the fan, because if you just turn off the fan, sometimes it'll come down slowly, right? And suppose you want to stop it immediately, physically, it's a bad idea to go and touch the tip of the blades, because it is going really fast. You can chop your fingers off. What is the best thing to do? Hold it somewhere close to the center. So put your hands inside somewhere close to center and you can stop the fan. I have done it.
You've done it? You've done it before?
Yeah, I've done it.
Let's get a giant. Do you have a ceiling fan? Can we try it out?
I feel like your hands are like your fingers are caught. But
Wait, we try like a wheel.
I mean, you don't have to dig in all of a sudden. You can just start touching and then it'll slow down faster. But the other one, touching, can be dangerous because it's moving fast. Why I had to do it, I'll tell you why. Because my son has 2 birds
Oh,
in his room.
no.
My son has 2 birds in his room, and I built up a nice cage for him and for the 2 birds, and they're very lovely birds. They're budgeriars. They're budgeriars, but they're so friendly. Like, you can just call them and they come and sit in your hands, put them there, put them on your head. Yeah, they're very good. Yeah. So, well, there's a ceiling fan in that room where the thing is. So occasionally, he removes he opens the thing, and then they are free to fly around inside his room. So we make sure that it's not going anywhere else but inside. So if you want to kind of pet it, you just get into the room somehow and close the door so that it doesn't go anywhere in the house. So what happened was, one day I didn't realize that the birds are out. It was quietly sitting somewhere, but I didn't realize it. I just went in and I turned the fan on, and then after some time, when I looked, the birds started flying. When the birds started flying, immediately I saw the fan as a big danger. It's definitely a big danger because they have a tendency to go to the fan normally. And they don't like black color. So normally what we do is we put some black socks or something like that on top of the fan, so that they will be like afraid to go there, to just repel them off. Now, when the fan is, of course, spinning, they don't see anything there. So they may fly right in. So therefore, I suddenly realized the danger, and they already started flying, and the only thing I could do, there was a bed there, so I could jump onto the bed. So I just jumped onto the bed and boom, stopped suddenly. Because I want to stop as soon as possible because I don't want any part of it to be hit. It'll be done if it is hit. Yeah.
Is that why props are black?
Yeah, so birds.
I don't know. Because, yeah, maybe. I don't know.
Can I research this real quick?
You can.
We'll look this up.
Yeah, the props are black.
What about wooden props?
The spinny things on the plane.
Are they?
Plane goes like this. The little spinny thing right here reads.
Shiny. All right.
I was expecting to read.
Are all the props black? Wood, maybe it's still dark. It's not like light wood. All right, let's leave that aside. So the tip of the fan blade is definitely moving fast compared to the central part. because the omega is the same, but the radius, so the speed, linear speed is proportional to the radius. So the one which actually is moving, the one at the outer end is going to be definitely moving faster. And the one right in the center is literally not moving. If there is any dirt or something on the fan, on the central hub, you can actually literally see it going. But you won't see the same thing on the tip. The tip is moving really fast. Okay. All right. Good there. Now, looking at this one, the velocity here is v1 and the velocity here is v2. Is the velocity changing?
Yeah.
So is there an acceleration?
No.
No? What is the definition of acceleration? Rate of, then how can you just now said there is a change of velocity, and then now you're saying there's no acceleration. There is definitely an acceleration. Without that acceleration, you're not going to be able to change the direction at all. How can you change the direction of something? Like soccer ball is coming from there. And can that soccer ball automatically just deflect and go there? Even if it is going at the same speed, 10 meters per second, 10 meters per second, magically change directions. How can something do that? What is required to be applied on the ball? F force. And what does the force cost? So it is definitely acceleration involvement. So if a ball is going from there and changing directions, there is an acceleration. Without that acceleration, change of velocity or change of direction is not possible. Even here, there is an acceleration. So what is the acceleration definition? Acceleration is defined as final velocity minus initial velocity over time. That is the definition of acceleration, what I've written there. In this context, acceleration is v2, vector v2 minus vector v1, because that's the final and that's the initial from here to here, over t. So it's v2 minus, how do you do v2 minus v1 vectorially? How do you subtract vectors? Add the negative of v1 to v2, right? Isn't v2 minus v1 the same as v2 plus negative of v1?
Yeah.
And how do you draw it? First draw v2. Here is v2. I'm going to magnify this a bit. So that's v2. And where is negative v1? Downward. And I do it from here. That's negative v1. So where is the resultant? Where is v2 minus v1? That is v2 minus v1. So if v2 is directed like this and v1 is directed like this, which way is v2 minus v1 directed? Which way? Look at the direction. Copy that. Copy this direction.
To the center.
So acceleration is directed always to the center. The acceleration is directed always to the center. Very important concept. It's always directed towards the center. And that acceleration is called, anyone knows it? Centripetal acceleration. Correct. So the acceleration is called centripetal acceleration. Some books write it as C. So it's v2 minus v1 over time. And some books write it as R, radial acceleration, the same thing. So this is centripetal acceleration or radial acceleration. Why is it called radial? Because that acceleration is along the radius. The acceleration is along the radius, wherever it goes. That's why it's called radial acceleration. But there's another term for it, is centripetal acceleration. So all centripetal accelerations are radial. Okay. Now, to find the magnitude of that acceleration, we need to find the magnitude of this arrow. How much is the magnitude of that arrow? What's the size of that arrow? In terms of size, now we are looking for the size. We know the direction is towards the center. For the size, look at this picture. This angle theta is a very small angle. And so the angle comes out here. It's a small angle. And why is it a small angle? Because acceleration is defined as rate of change of velocity. We don't want to wait minutes for this change of velocity. The change of velocity is taking place every microsecond. Every microsecond is changing. So we are looking for the rate of change for the smallest possible time. How much is the change taking place? That's what we do. So it will give you the instantaneous acceleration at that spot. So we don't want to wait for it to go from here to do this calculation. It's always here. This angle that I've shown is too big. This angle is supposed to be very small. If this angle is very small, what's the magnitude of this side and the magnitude of this side? What are they? They're equal, right? So this side is V. This side is also V. And this is a small angle. It's so small that I can consider this to be an arc. Are you able to get there? It is so small that a straight line or an arc won't make a difference. Right? When the angle is very small, a straight line or an arc won't make a big difference. Like for example, we are here. Downtown is there. On the earth, where are we and where is downtown? So close, right? So on the real earth, if you're going to draw an arc or a straight line, will they be different in length? Pretty much the same thing. Only when the distance is too much, then yes, there will be a big difference between the chord and the arc length, right? Yeah. But for small angles, the chord length and the arc length will literally be the same. So this is like an arc. So you can use the formula that you learned earlier. How do you find the arc length? S is equal to r theta. Look at that. This is your S. This is your S equal to r theta. Isn't this like radius? This is like the radius. So S is equal to r theta. And therefore, V2 minus V1, the magnitude of V2 minus V1 is r theta. Oh, not r theta, but V theta. This is equal to V theta. So if I substitute that over here, I will be able to get the acceleration's magnitude. If I want to get the magnitude, I will take this and substitute it right there, so I get V theta over T. So the acceleration, centripetal acceleration. See, when I remove the arrow, it's like saying the magnitude. So when I say AC, that's just the magnitude. Instead of putting the arrow and putting the two bars across it, if I just knock off everything, if I write like this, it means the same as that. Okay? If I just write the letter, it means only the magnitude. Yes?
Why is it V theta?
V is like the radius, and the angle is here. Because imagine this one is similar to this. S r theta. So S is equal to r theta, this is equal to V theta. Okay? Now, what is theta over T? Huh? Omega, not W. So V omega. So we have an equation for centripetal acceleration, which is the linear speed times angular speed. Linear speed times angular speed is omega, centripetal acceleration.
Yeah.
So centripetal acceleration is equal to v omega. But what is v? Isn't v equal to r omega? Substitute this here. What do you have?
R omega squared.
R omega squared. Again, centripetal acceleration is v omega. But what is omega? V over? Isn't omega v over r? Substitute it here. What do you have? So centripetal acceleration comes in three different equation formats. V omega, also centripetal acceleration. R omega square is also centripetal acceleration. V square over r is also centripetal acceleration. This is most commonly used, that one. Because normally we talk about speeds, right? So this is very commonly used. This is also used after. If you're talking about angular speeds and all that, then yes. This is very seldom used. So this equation is not very much used because it uses linear speed and angular speed. Normally, it is not a common equation. But this is the equation that we start with. And then we obtain these equations. So this is the most commonly used equation for centripetal acceleration. So what is this centripetal acceleration now? It is the acceleration required for any object to go round and round in circular motion. Without that acceleration, the object cannot change its velocity. It cannot keep going in circular motion. Do you get it? Centripetal acceleration is required for any object to go round and round in circular motion. Failing to provide that centripetal acceleration, the object cannot maintain its circular motion and then it will just fly off. So what is needed for an object to go round and round circular motion? Centripetal acceleration. Now what will provide that centripetal acceleration? No. A centripetal force. So what is centripetal force? Centripetal force is a force that is needed to keep an object in circular motion. Centripetal force. Centripetal force is the force needed to keep an object in circular motion. And it is always directed towards the center of the circular path. Write it down. Centripetal force is a force needed to keep an object in circular motion and is always directed towards the center of the circular path. If you know the acceleration, how do you find the force? F is equal to ma. So that same thing you apply here. So what is centripetal force? Centripetal force is take this acceleration and multiply by mass. Mass times acceleration, Newton's second law, comes in here. So the acceleration is not only when something is going in a linear path, it can also happen in a circular path. You need it. Centripetal force is mass times velocity square over, or you can also call it mr omega square or mv omega. All of them are right. Centripetal force is equal to all this. You need a centripetal force for something to go round and round in a circular path. Look at these keys. The keys are now going in circular motion, right? What is keeping this key in circular motion? It requires a force. What is providing the force here? Someone tell me that correctly. What is changing the velocity direction of this key continuously? What of the linear? What? Tension. So there is a force pulling it like this along this direction. Which way? Towards the center. And that force is a necessary force for this to keep going round and round. Now if this is going like this, same thing. There's a tension pulling it towards my hand. I am continuously pulling it. That's why it is going round and round. Now what if the thing breaks all of a sudden? Now if it breaks all of a sudden, the tension is going to be missing. So what will happen to this key? Will it start going in bigger and bigger circles? It just flies straight off. So what's happening is if it breaks over here, this velocity will stay the same. Nothing is there to change its velocity, so it will keep going straight. It just flies off straight. Do you get it? So what provides a centripetal force for this key to go round and round? Tension. Directed towards the center. What keeps the moon in circular motion around the earth? Gravitational force. No tension. There's no cable attached. Gravitational force. The force of attraction from the earth on the moon is what kind of keeps it going in circular paths. So the moon is changing direction continuously because of the pull of the earth. What takes the earth in circular motion around the sun? Gravitational force. What takes the earth round and round is gravitational force. So if the gravitational force is missing all of a sudden, it will just fly off tangentially. What keeps an electron going around in a approximately circular orbit around the nucleus? Electrostatic force. Nucleus is positive, electrons are negative. So there's an electrostatic force between the two. So the electrostatic force is what keeps it going in a circular path. Now, which orbit they spin, how fast they go, they're all decided by these rules. So if you dig more into the Bohr's, which radius and all that, you will see that circular motion comes in and you'll start applying these equations. You'll apply these equations right there. Yes.
When you're talking about forces in regards to circular motion like gravity, then do you consider gravity a centripetal force, or is it still just gravitation?
On us right now?
No, like when you're talking about how it keeps something going.
Yeah, if it is orbiting, yes, gravitational force is the only force.
No, but like then you call is it like do you consider it like a category of centripetal force?
Gravitational force, no, the centripetal force is provided by the gravitational force. You get it now? Some force is needed to keep it going in a circular path. Now, watch this. I'm going to walk and I'm going to turn around there and watch what I'm doing and I'll ask you questions. Watch. Did I take a turn somewhere?
Yes.
Where?
Right
Right here. What made me take that circular motion? What force changed my direction continuously?
The ground against your feet.
Yeah, they're trying to get your foot that direction.
You were pushed by
Really?
Your left foot
Towards this
harder than the right foot.
It's a force that way, right? You're right. The force, because I'm taking a turn like this, the center of that turn is here.
Yeah.
So definitely there's a force in that direction. But who pulled me from there? It's not gravitational force.
electromagnetic.
All right, now.
Not the answer.
All right, imagine I'm trying to demonstrate that walk again and Alex threw some oil on the floor.
Come on, Alex.
And I'm walking like this, and I'm just hoping to turn. What will happen to me?
You'll slip.
So what actually takes me around? Frictional force on my feet this way. Yeah, it's the friction that actually helps us to make our turns possible. What provides a centripetal force for a car to take a roundabout? Friction.
So that's why tires are made of rubber, which is
Yeah.
high coefficient of friction.
Good coefficient of
Then
friction.
can make-
Now, what happens when your tires are sort of worn out? You won't get the required friction, and so it can skid. It will skid. Now look at this equation and then see this. Centripetal force required towards the center for anything to go around in a circular path depends on what factors? Number one, that means if it's a massive car taking a turn, you need a lot of friction there. If you don't have a proper grip, it can skid and go. Biggest component is this, because it's getting squared. Because it's getting squared, that factor is a very, very important factor, the speed. If you're going at a certain speed around a turn, and if you go faster, the requirement for centripetal force is going to be increased, tremendously increased. If you go twice as fast, you're expecting 4 times the centripetal force from the road as a grip. Remember, the grip by the road on your tires has its limits, right? That's called the limiting value of friction, mu s times the normal force. Mu s times the normal force, that's the limit. Now what will happen if you cross those limits? Friction will say, I'm gone, so you go now. Alright, so what keeps you going around in circular motion is friction. That's why, imagine you ride a bicycle every day on a certain road. Imagine you're riding a bicycle every day on a certain road. Take the turn. Normally, every day you do it fine. What helps you to take a turn is friction, obviously. But one day, when you're going, before you went there, a sand truck kind of dropped some sand on the road, and you didn't realize that. And you're just going casually the same way, and then you take a turn, and you pay the consequence for that. What happens then is the coefficient of friction between your tires and the road has gone down, which means you need to go slow. And if you keep going at the same speed, friction says, I cannot provide you all the friction, you keep going now. So you just skid and go. You'll fall. Obviously, when this thing falls, when you're trying to take a turn and friction is not helping you to stay there, you just trip and fall. Now, on a snow day, you'll experience that on your car. That is why speed is an important factor. Well, can you drive on an icy road? Yes, but you've got to be extremely careful with the speed, because the change of lanes or the change or a circular road, unless you go slow, friction between the tires and the snow or the ice won't be able to provide the necessary centripetal force for you to go round and round circular path. And so immediately slipping is the option. Slipping happens. So why people actually generally skid on the road is because of this. They're going at 60 miles per hour, and all of a sudden they see some kind of danger. Even though the road is good conditions, they see some danger, immediately they turn. And if they turn, they're making a turn of a certain radius. So they are expecting some friction to really help them make the turn. Most of the time what will happen is, because they're going at tremendous speeds, the friction requirement is exceeded. So you take a turn, immediately you start skidding. So the very purpose of your turn is to get away from that scene, but you're not going to get out. You're just...
What makes you flip? The center of gravity being high?
Flipping is actually, yes, because center of gravity is higher up. So we are going to talk about that later. Flipping action. Why? And what is the condition requirement? How can you prevent it? And what angle can you do all that stuff? We'll talk about it.
When you go like on exit ramps and you're driving and you turn like in the turns, why do you swing to the side so far?
We're going to talk about all those things in the next class.
So you look like a
We're going to talk about all those things in the next class. All right?